Okay, welcome to our first lecture on kinetics, which is a hugely important area that we'll be talking about maybe for the first time for some of you. So the question of kinetics is really important for elucidating reaction mechanisms. So in your previous classes, you talked about reaction mechanisms, but how do we know which mechanisms are in operation? So one example, which you'll have seen from organic chemistry, you'll have seen for nucleophilic substitution reactions, you have two possible mechanisms. There's SN1 and SN2. So here's SN2, and then we'll do SN1 over here. And then so you'll have seen before for SN2, one example, let's say if we take butyl iodide, and then we add methoxide to it, right? SN2 is where it attacks, and then we lose the iodide. And then this proceeds through this transition state, where if I kind of draw it, like here is my carbon, H, and then we'll have our kind of propyl group hanging off here, 1, 2, 3. And then our transition state will have both substituents on there, so the iodide and the methoxide. And you depict the transition state, so this will be negatively charged, as this double dagger notation. And then this will give us our product, which is the substituted methyl ether. So this is our overall reaction. And so this is the key part of SN2, that we have this transition state. For SN1, on the other hand, if we start with a tertiary halide, and we go to we add methoxide, for example, we still form the substituted product, but this proceeds by this dissociation of the bromide anion to form this carbocation intermediate plus bromide, and then the methoxide over here then comes in and attacks to then form that same product. So this is SN1, and then the key part about this is that this species, this carbocation, is an intermediate. So the difference between intermediate and the transition state is the intermediate might be observable or isoluble potentially, whereas transition states you can't observe spectroscopically because it has such a short lifetime that it's almost impossible to see. And the key part is if we can compare these by reaction coordinate diagrams, if we think about the energies of these species. So here's, I'll do this in blue, energy. And here's our reaction coordinate. So here, again, we have our starting material energy. Starting material, we have our product, right? So thermodynamics is, here is delta G. But in this case, the energy, the pathway of this reaction really matters. So in this case here, we have some hump. So this species is our transition state. So this is our transition state. So it's this transition state here is what we're seeing. And this is of some energy that's higher than the starting material energy. So overall, over here, this energy over here is the so-called activation energy. And then so the nature of this pathway, this yellow curve here, as well as the activation energy, is what we see in kinetics, and that tells us mechanism. Knowing the starting material and the products does not tell us mechanism. So if we were to compare to the exact same reaction coordinate diagram for SN1, so again, reaction coordinate, E, oops, here's E, not potential, this is energy in this case, so it might get a little confusing. So here, if we again have the starting material and the product, for the SN1 mechanism, you might have seen that there's this kind of dealio here. And then so this state here is the intermediate. So it's this guy. And then so it's at a local minimum, which is why it has some finite lifetime that we might be able to observe it using NMR or other spectroscopic techniques. And then so these, for SN1, we have these two transition states. So transition state 1 might look something like, if we're thinking about the dissociation of bromide, transition state 1 might look like where the bromide is starting to leave. And then we have delta minus, delta plus. So this is one transition state. And then transition state 2 is this bond-forming transition state. So our transition state 2 could be something like where the methoxide's coming in. And again, we have delta minus, delta plus. So the key part about kinetics is that it tells us the nature of the transition states that are important for the reaction that we end up doing. So that's how, to be able to measure these pathways is what's critical for, and the reason that we do kinetics, to be able to figure out how things are forming bonds or breaking bonds. And then so what kinetics gives us is it gives us reaction order, and rate law, or constants. We'll talk a little bit more about what this means, but you'll see here that in this transition state for SN2, we have both the methoxide and our starting material interacting. So what we'll see later is that our rate for SN2 is going to be equal to some constant, and then the concentrations of both the butyl iodide and the methoxide matter for the rate. In comparison, our rate for SN1 is only going to be dependent. Our transition state here, transition state 1, is only dependent on the concentration of this butyl bromide. So it's only going to be dependent on this. So we'll discuss this a little bit more in subsequent videos, but this would be what's called the second order reaction for SN2, because we have two things, and this is what's called the first order reaction. So by measuring kinetics, aka how fast the reactions go under different conditions, we can distinguish these two mechanisms and get information out about the transition state and our pathway for how reactions perform, and therefore elucidate mechanism.